Hello, this is Aryan Chaudhary. This is my physics lab 1. This is a constant velocity problem. So in this experiment we'll discuss five main things. First is the introduction, which has the objective. Second, the motion analysis of a ping pong ball using tracker. Third, I'll compute a model for the motion using GlowScript. Third, I'll compare the actual and predicted motion. And fifth is the analysis and the error analysis. So the objective. In this experiment, I would attempt to track the motion of a ping pong ball moving at constant velocity and zero net force using tracker. Then I would make a computational model for this using GlowScript and then compare it with the observed values. Some of the key ideas in this experiment: Newton's first law. An object would remain at rest or at uniform velocity unless acted upon by an external unbalanced force. Newton's second law: force is equivalent to mass times acceleration. Since in this case the net force is zero, the velocity should ideally be uniform. Hence, the graph that we should obtain of position versus time should be a straight line. In this case, the system is the ping pong ball, and everything else that interacts with it is the surroundings. So the procedure for the experiment is as follows. I would give a ball a small push at the beginning, and its motion would be recorded at 240 frames per second using a smartphone camera. Then I will do the motion analysis of the video using a tracker. For the calibration, I'll use the standard diameter of a ping pong ball, which is 0.02 meters. And the mass of the ball is 0.0027 kgs, which is also standard for all ping pong balls. Only motion in the x-axis would be considered. So this is me tracking the video using tracker. As you can see, I put the start frame of the tracker at the middle of the motion so that the velocity is constant, since in the beginning it's accelerating. And as you can see, I got a straight line since the velocity is more or less constant throughout. Now, computing a model for the ping pong ball. From the data that I collected from the tracker, I used the formula. I've used the formula below to calculate the initial velocity. Here, the RF is the fifth data value, and R initial is the first data value, which came out to be, and the average velocity came out to be 0.649925 meter per second. The initial conditions and other parameters of the code were as follows. I put the mass of the ball, then the initial position was shifted according to the one obtained from the first data reading from the tracker, and the velocity of the ball was put as the initial velocity that I obtained before. For the computational model, I used two main formulas, the position update and the velocity update formulas. So this is the code that I put in the computational model. The time of my experiment was 1 second, and since the f net is 0, the velocity should remain constant. It shouldn't change. So this is the graph that I observed, graph of position versus time for the observed and the predicted motion. As we can see, a few key observations that we can make is the observed value, they match the predicted motion for the first few seconds, but then they start to deviate away from the predicted values because as air resistance and friction comes into play, this causes a dampening of the motion, causing the velocity to slowly and gradually decrease. In an ideal environment, however, the ball's motion would follow the predicted trend, and it would not stop since there would be no dampening motion. So for the conclusion, there are a few questions that I have to answer. What if the axes were flipped? If they were flipped, this would make the slope of the graph negative, and I would get a negative velocity since the direction of motion is now in the negative x direction. However, this would have no effect on the conclusion of the experiment. Is it possible for me to say how many pushes or pulls are added to give you net zero force? I don't think it's possible because in the case that I observed, there was not a net zero force. After the ball was released, friction still acts on the ball in reality, which means throughout the motion there was a decelerating force. For the error analysis, there were some errors. For example, the ball was tracked manually, which affects the accuracy of the values due to human error. And since this is not a isolated system, there are other forces like friction, which dampen the motion of the ping pong ball, and uniform velocity cannot be maintained. Thank you.